Hi, and welcome to our discussion of measurement systems. This time we're going to talk about hygrometry. Hygrometry, by definition, straight from the glossary of meteorology, is the study of humidity in the atmosphere and how we can measure it. It comes from two Greek words, metron, which means measure, and hugros, which means moist. So first we're going to look at humidity variables. So we're going to talk very generally about water in the atmosphere. This is kind of a review, something that you probably had in other classes in meteorology. And after that, we're going to work our way into the ways that we measure or we describe water vapor in the atmosphere, what we call moisture variables. So first, what is water? This is the definition straight out of the glossary of meteorology. It says that water is a transparent, colorless, odorless, and tasteless liquid found near the surface of the earth. In Grand Forks, I don't think that holds true, especially in the springtime. There's definitely a taste, typically from chlorine, and also sometimes it's colorful, especially when they start cleaning out or flushing the water lines. But there's the definition of water. And water can exist in three different phases. You probably learned this in grade school. Three different phases in our atmosphere. You can have a solid, which of course we call ice. Liquid typically is known as just water. And then the gas, we call that water vapor. So we're more concerned in meteorology about water vapor and the measurement of water vapor. So we have lots of different types of systems that can measure water vapor or the amount of water vapor. And water vapor, of course, is water that's in the gaseous form and in our atmosphere, and it can act as an ideal gas at certain temperatures and certain pressures. But as you get closer to saturation, it starts acting weird, and we'll talk a little bit about that here shortly. But it is a variable constituent in our atmosphere. We typically say that there are stable gases in our atmosphere. You know, the atmosphere is made up of oxygen and nitrogen and argon, and those are pretty fixed in the amount of those constituents in our atmosphere. But water vapor is a variable constituent, meaning that in some locations you'll have very high water content or water vapor content, and other places it'll be very low. Depends upon your source of water vapor. Are you close to a body of water, or are you out in the middle of the desert? Typically, water vapor makes up not more than 4% of the atmosphere, and sometimes it can be very close to zero. This brings us to Dalton's law. Dalton's law is basically the law of partial pressures. Dalton lived back in the 18th century, and he came up with a concept saying that the total pressure of a mixture of gases, now a mixture of gases meaning several different types of gases all mixed together, such as oxygen, nitrogen, argon, water vapor, carbon dioxide. So the total pressure of the mixture is the sum of each pressure of each gas if it occupied that volume all by itself. So that means that typically our pressure at sea level is pretty close to 1,000 millibars. And if that's the case, nitrogen usually makes up 70% of our atmosphere, so the pressure exerted by nitrogen is about 780 millibars. Oxygen is 21%, so that'd be about 210 millibars. And then water vapor, of course, is variable. If water vapor is only 1%, then it would make up, or it would exert 10 millibars of pressure for a total pressure of 1,000 millibars. So water vapor pressure is the pressure that's exerted by water vapor molecules in the air. The number of water molecules in the air determines the pressure. And, you know, each water vapor molecule has mass, so the more water mass in the atmosphere, the more pressure that it exerts. And this picture kind of shows you, or this diagram shows you that concept, where we have a container with liquid water and a vacuum above that. Over a period of time, water vapor molecules will leave the water surface and start to fill up that vacuum. So you'll have water vapor molecules in the gaseous form and liquid water in the liquid form. And we can measure that pressure, or we can actually calculate that pressure. So if there's not many water vapor molecules in the atmosphere, they're exerting very low water vapor pressure. The more water vapor molecules in the atmosphere, over a period of time, you'll have more and more leave the water surface and fill up that vacuum. And since you have more water vapor molecules, more water mass, they're exerting more pressure, a higher water vapor pressure. There comes a point where the number of water vapor molecules in the air reaches its limit, and the water vapor molecules will start to return back to the water surface. We call that point the saturation point, and we can measure its pressure, and that would be the saturation water vapor pressure. So by definition, the saturation water vapor pressure is the pressure that water vapor molecules would exert if the air is saturated. And we also say that it reaches equilibrium, and that's at a given temperature. It happens at a given temperature. So, in other words, if you heat up that water, that liquid water, more and more water vapor molecules would leave the water surface and go into the air. There would be eventually so many that you'd have the same number leaving the water surface as returning back to the water surface. So we say that it's at equilibrium and the air is saturated with respect to water. This can happen at any temperature. As you increase the temperature of the water, more water vapor molecules leave the water surface, and you have a greater or higher water vapor pressure in the air, saturation vapor pressure. Keep increasing the temperature, more water molecules leave. Eventually there's an equilibrium at that temperature, and the pressure is higher. The water vapor pressure is higher because there's more water vapor molecules in the air, greater mass of water in the air, water vapor. So that's the concept of saturation. It depends upon temperature, and this is not a linear curve. The curve actually is somewhat exponential. You can also do this for ice. There is a saturation vapor pressure over ice. Since ice molecules don't leave the surface, the solid surface, very easily, it takes fewer water vapor molecules to saturate or reach equilibrium. Not many leaving, not many returning. When the number that are leaving equals the number that are returning, you have saturation, and that is saturation with respect to ice. So that is your saturation as a function of temperature also, but you'll only see this at temperatures colder than 0. And that's what you see on this diagram. You see a separate saturation vapor pressure curve for ice compared to water. And of course we said that it occurs at lower vapor pressures because fewer molecules are leaving the water surface to reach saturation. You can also use an equation to figure out the saturation vapor pressure for liquid water. And this equation is, there are many different equations that are very similar to this. This one is called Teton's formula. And in this case, the temperature needs to be in degrees Celsius. And when you calculate it, you get pressure in millibars. Some numbers that you should remember: at 0 degrees Celsius, the pressure exerted by water vapor molecules at saturation is 6.11 millibars, and at 100 degrees Celsius, it's 1013 millibars of pressure. So stick in the numbers. Here's an example. Stick in 10. If you do the calculation, you should end up with 12.3. You should try this and practice this because you'll have to be doing this on homework and also on exams. Most times in our atmosphere, the air is not saturated with respect to water vapor or with respect to liquid water. There's less water vapor in the air than could be. And When that occurs, we say that the air is subsaturated. Looking at this diagram, it shows the saturation vapor curve. And if we just look at one particular temperature, say for a nice spring day, a temperature of 60 degrees Fahrenheit, the saturation vapor pressure amount might be much higher than the actual amount of water vapor in the air. And that makes sense, that we don't always have 100% relative humidity. Typically, relative humidity is lower, so we say that the actual amount of water vapor in the air is less than the saturation amount. That's all I have for this video. We'll come back and talk about water vapor variables in the next video.